Welcome to a lesson with Dr. Powell. Let's take a look at finding the volume of a solid defined by cross sections. Suppose our cross sections are equilateral triangles and they're drawn this way. So we're cross cutting this way across a base. So we're kind of putting this cross sections on a base here in the XY plane. That's between the line y, the curve y equals square root of x, the x-axis, and going from 0 to 1. Now, notice that because we're taking cross cuts like this cross-sectional area is the derivative of volume growth with respect to y, as we're kind of going from here in this direction. And so when we want to set up an integral, we're setting up an integral that'll go from in y from, now notice that this point right here in y is actually 1. So really our interval of integration is from 0 to 1 with respect to y. Now, what do we put into the integral is we put in the derivative of the volume to find the change of the volume, since the volume starts at 0 and then it builds up to here. So the derivative of the volume is just the area of that cross section. What's the area of this cross section? Well, we take, it needs to be arbitrary, it needs to be a function of y, so it needs to depend on an arbitrary y here. So we pick a representative y in the middle where y is still a variable, and we see what's going on with it. So at this particular position y, we know that the x value right here is y squared. We know that because this is on the curve y equals square root of x, and if we solve for x, we get this. So we get y squared is right here, and then over here we know this is 1. So the total length from here to here, which is the base of the equilateral triangle, is 1 minus y squared. Now we can find the area of the equilateral triangle by realizing that all the sides are 1 minus y squared. So this is the hypotenuse. If you take this hypotenuse, if this hypotenuse were just 1, then this height would simply be the sine of pi thirds. However, similarity of triangles, just multiply all the sides by this quantity. So the hypotenuse is this, but then this becomes the height, which is just simply this, 1 minus y squared times sine of pi thirds. Sine of pi thirds is √3/2. So this right quantity is the height of the equilateral triangle. Take your height, multiply by your base, and multiply by a half, and this gives you the area of that equilateral triangle at position y. So really, volume has now turned into a calculation of just areas, and then you just integrate that. So we have this area, and we can put it into, and we can integrate this. Now, when we put this into the integral, which is what I've done here, I've simplified things a little bit. I've multiplied the √3/2 times a half to get √3/4, and I kind of factored it out of the integration, just as you would factor a constant out of a derivative calculation or an antiderivative calculation. So I put it here, and then further, then I multiplied 1 minus y squared times 1 minus y squared to get this. Then I'm integrating from 0 to 1. Keep the constant on the outside, and then you integrate the y, that to y, you integrate that term and that term. You've put in a 1, you put in a 0, you subtract. When you put in 0, in this case, it's just 0, so it's just as if we just plugged in 1. And if we do that, we end up with this particular volume. Thanks for watching.